Thank you for joining today's ARSET training, NASA Satellite Laser Altimetry for Coastal and Nearshore Bathymetry. I'm Sean McCartney from NASA Goddard Space Flight Center in Maryland, serving as your ARSET trainer. I'm excited to begin this first part of our comprehensive two-part satellite bathymetry training with all of you. For newcomers to ARSET trainings, the following slides present a short program introduction. The Applied Remote Sensing Training Program, or ARSET, part of NASA's Earth Action Capacity Building Program, offers free, accessible training on remote sensing technologies, methods, and applications. ARSET's mission is to increase Earth science remote sensing and model data use in decision-making by providing training for professionals in the public and private sectors, environmental managers, and policymakers. On the right of the slide, you can see all the different thematic areas in which we conduct trainings. ARSET offers both online and in-person training sessions designed for beginners through advanced users. All trainings are provided at no cost through live instruction, instructor-led sessions, or self-paced formats like the Fundamentals of Remote Sensing course on ARSET's Learning Management System. Materials are available in multiple languages and can be freely used and adapted for educational purposes. Users of ARSET methods and data should acknowledge the NASA Applied Remote Sensing Training Program. Additional information is available on our website. The following slides provide an overview of the two-part webinar series, NASA Satellite Laser Altimetry for Coastal and Nearshore Bathymetry. So why would somebody want to take this training? Well, nearly 80% of the world's oceans are unexplored and unmapped. Successful coastal management depends on monitoring and mapping. Coastal bathymetry is essential for navigational hazards for vessel operations, tidal modeling and prediction, tsunami risk assessment and forecasting, underwater cultural heritage preservation, and environmental change monitoring. Satellite-derived bathymetry enhances capacity for collecting high-resolution, accurate depth data supporting varied applications. By the end of this two-part training, participants will be able to identify NASA bathymetry data used for global, coastal, and nearshore bathymetry mapping for risk reduction relating to shipping and navigation. Identify the applications and limitations of ISAT-2 bathymetry data, ATL24, for coastal and nearshore bathymetry mapping. Plot and download ISAT-2 bathymetry data using SlideRule web client, and analyze ISAT-2 bathymetry data using SlideRule Python client. The prerequisites for the training are two ARSET courses, Fundamentals of Remote Sensing course, and Mapping and Monitoring Lakes and Reservoirs with Satellite Observations. From December 2nd to December 4th, there will be two 1.5-hour sessions, which will include presentations, demonstrations, and question and answer sessions. All materials and recordings for each session will be available from the training webpage. If you are not able to attend one part, a recording will be made available within 48 hours on the ARSET training webpage. Homework opens on December 4th and will be due on December 31st. You will be able to access the homework from the training page on Thursday, December 4th. A certificate of completion will be awarded to those who attend all live sessions and complete the homework assignment by the given due date. Part 1 of the training is focused on NASA ATL24 Bathymetric data for coastal and nearshore applications. The objectives of Part 1 of the training are as follows. By the end of today, participants will be able to identify NASA bathymetry data used for global, coastal, and nearshore bathymetry mapping for risk reduction relating to shipping and navigation, identify the applications and limitations of ISAT-2 bathymetry data, ATL24, for coastal and nearshore bathymetry mapping, and plot and download ISAT-2 bathymetry data using SlideRule web client. Please put your questions in the questions box, and we will address them at the end of the webinar. Feel free to enter your questions as we go. We will try to get to all the questions during the Q&A session after the webinar. The remainder of the questions will be answered in the Q&A doc, which will be posted to the training website about 1 week after today's training. It is now my pleasure to introduce the guest trainers for today's webinar, Dr. Lori Magruder, Dr. Diane Fritz, and Joseph Paul Swinski. Lori Magruder serves as Associate Professor in Aerospace Engineering at the University of Texas at Austin, with previous roles at Jet Propulsion Laboratory and Johns Hopkins Applied Physics Laboratory. Following 9 years of science team leadership on NASA's ICESat-2 mission, encompassing mission development, implementation guidance, and operational instrument pointing strategies, Magruder has transitioned to leadership positions on additional remote sensing science and instrument teams. Diane Fritz holds the position of Associate Scientist at the National Snow and Ice Data Center, NSIDC, located in Boulder, Colorado, and serves as a remote sensing educator at the University of Colorado. Her academic credentials include a doctorate in geological sciences. J.P. Swinski is a 24-year NASA Goddard software developer who spent most of his career creating flight software for spacecraft and science instruments. He led flight software development for the Atlas instrument from 2010 to 2016. In 2018, he transitioned to cloud-based data processing solutions, and in 2020, co-developed SlideRule with the ICESat-2 project scientist and University of Washington, which is a public web service providing fast cloud access to ICESat-2 data. Lori, over to you.
Thanks, Sean. I'm so happy to be here and talk about ICESat-2, the new bathymetry product that has just come out earlier this year. I can honestly say that ICESat-2 is my favorite satellite, and I've worked on it for many, many years. And so this is just a really exciting time for me to be here and provide an overview of the mission and an introduction to the ATL24 coastal and nearshore bathymetry product. So let's start with the mission overview. The Ice Cloud and Land Elevation Satellite 2 is an Earth-observing laser altimetry mission that launched in 2018. So we've been on orbit for a little more than 7 years. It completed its prime mission and successfully satisfied all its science requirements in 2021. But all operations are still nominal, and it's continuing to give us amazing data. ICESat-2 carries a single instrument called ATLAS, the Advanced Topographic Laser Altimeter System. ATLAS is a photon counting laser altimeter, meaning it's sensitive to single photon reflections from the Earth's surface. This state-of-the-art technology to date has produced over 2 trillion laser pulses. Turns out that's a whole lot more than the 2 billion from the original ICESat mission in 2003 to 2009. Right now, the prediction is that ICESat-2 has all consumables on board, meaning laser energy and fuel, to continue operating until 2033. So ATLAS uses a neodymium-doped yttrium orthovanadate laser to produce 6 individual beams that's configured into 3 beam pairs that you can see in the schematic here on the slide. Each pair contains a weak and a strong beam with respect to laser energy at a 1:4 energy ratio. The pair components are separated by 90 meters in the cross-track direction, and the pair-to-pair separation is 3.3 kilometers. Each of the 6 beams provides an elevation profile of the illuminated surface with around a 12-meter diameter footprint. So these are just creating pencil lines of elevation across the Earth's surface. ATLAS output wavelength is a 532 nanometer, which is in the visible green part of the spectrum, and a pulse width of 1 nanosecond, which speaks to the high vertical resolution of the system. Photon counting altimetry allows some unique advantages in terms of data collection. So since the receiver is sensitive to single photons, it allows the system to operate at a lower energy level compared to previous or other types of LiDAR technology. In turn, that means that the system can pulse at a faster repetition rate. And in this case, ATLAS has a 10 kilohertz repetition rate that at the altitude, which is about a 500 kilometer average altitude, it can produce a laser footprint or puts down a laser footprint every 70 centimeters in the long track direction. The final thing I'll mention here in terms of the collection strategy is the fact that the orbital plane is inclined at 92 degrees from the equatorial plane, which means that the coverage for ISAT-2 goes from 88 degrees south latitude to 88 degrees north latitude. So I think it's important to get oriented with respect to what the ISAT-2 data looks like. So I'm showing you an example elevation profile over West Central Greenland. The horizontal axis is latitude and the vertical axis is the elevation. So each of these black dots indicates the ATLAS detection, a detected photon by ATLAS. Every photon has its own latitude, longitude, and elevation. So the challenge with photon counting is the need to separate the signal photons from the noise photons. So although in this case, it's pretty easy for us to look at the profile and identify the surface, which is this dense black line, it's a lot more challenging to automate the process of signal finding. Signal finding also differs greatly with surface reflectance, surface type, and surface feature length scales. So ISAT-2 provides data products for specific surface types that have been produced with unique algorithms optimized for the surface characteristics. So when we start to explore these data over the last 7 years on orbit, you can see through aggregation all of the impact that ISAT-2 has had with respect to the specific data products it provides. We see sea ice measurements both in the Southern Ocean and the Arctic. We see the land ice and mass change for Greenland and Antarctica. And next comes the brown, or the terrain, the land surface elevations, and then the vegetation canopy heights, which will be in green here in just a minute. Additionally, we have data products over the ocean and inland water surfaces. However, what was somewhat unexpected was the ability of ISAT-2 to measure beneath the water surface, or measure underwater topography, which is also called bathymetry. It's common knowledge that the green laser wavelength can penetrate water, but it was not fully anticipated that a photon counting system from 300 miles in space would perform as well as it does. You can see here an example of the bathymetry that we've been seeing for quite some time. It's sea surface, which is this dark black line horizontal on the elevation profile. And then underneath is the underwater topography, or bathymetry. In this case, we're at the Great Barrier Reef. Studies of this performance, or the capability of bathymetry, has happened in various locations. And ultimately, we know that ATLAS can measure bathymetry at up to 40 meters in depth for clear water conditions. Certainly it varies depending on where you are geographically. However, until this year, we've not had a dedicated bathymetry data product from the mission. I thought it'd be important to just show you a snapshot of the data products for ISAT-2. The level 0 and level 1 products are telemetry and converted telemetry products. The level 2 products are ATL03, which is the geolocated point cloud, and then ATL04, which are normalized backscatter profiles. ATL03 is the input to all of the level 3A products, and those are those blue boxes in horizontal or in the middle of the slide. These are a long track products produced from these optimized algorithms that I mentioned previously. These level 3A blue boxes include those data we saw from land ice heights, sea ice freeboard, land and vegetation, inland water, and ocean. But then you can see this, this newly added box here, ATL24, which is the long track nearshore coastal bathymetry product, which I'm happy to introduce to you today. As an introduction, ATL24 was developed by the collaborative team, my team here at University of Texas at Austin, Center for Space Research, Jeff Perry and Matthew Holwell, and our teammates at Oregon State University, Chris Parrish, Kiana Keefe, JP Swinsky at SlideRule, and all of the mission or project science office partners, Jeff Lee, Tom Newman, Dennis Felixson. We're all working together and released ATL24 on April 1st earlier this year. Ultimately, ATL24 is designed to provide the community signal finding and photon classification for sea surface and sea floor along global coastlines. We had the goal of creating a robust algorithm that could be successful at the global scale, provide appropriate corrections to the data and confidence values of the signal classifications, and then also a per point uncertainty. So these were the goals of ATL24 when we first initiated development, which was a couple of years ago. What I'd like to emphasize here is the significant challenge with developing a single algorithmic approach that could satisfy all of those product goals. However, to meet this challenge, we use a novel machine learning approach called an ensemble. The ensemble creates a robust capability in the environment that is highly variable. When you consider that everywhere there's a different bottom type, a different surface reflection, changing water turbidity levels, and sea surface conditions. So ATL24 also provides a confidence value for each photon that indicates an estimate of the classification fidelity. And then additionally, we correct this with an index of refraction correction. The inputs of the ensemble are classification predictions from several base algorithms. And when I say classification predictions, is that photon a sea surface? Is it bathymetry, or is it unknown? Right now, the ensemble gathers input from 6 distinct methods. And since the errors of each classification-based algorithm are uncorrelated, the ensemble is able to predict bathymetry from the combination of predictions from the base algorithm input. So this creates a scenario for the whole is greater than the sum of the parts, meaning that the ensemble performs at least as well as the best performing algorithm for a given location. Ultimately, we're taking advantage of the fact that a single signal finding algorithm cannot perform equally everywhere. So what I want to point out here in the upper right is just a granular, a transect that we pulled out, and it shows the different colors just below the area where the turquoise photons are those classified as sea surface, and the brighter blue photons are those that the ensemble predicts as bathymetry. And then I'll point out here this plot on the bottom right is each column is the F1 score of the base algorithms and the ensemble for predicting sea surface and sea floor. So the ensemble is the column in the middle, and then you have 3 base algorithms on each side, to the left and to the right. F1 score is a metric that we often use in combination with a lot of other metrics to understand how good we're doing in terms of accurately classifying the photons as sea surface or sea floor. So the green labels are each algorithm of how they predict sea surface. And you can see that each of those values is almost, they're pretty equal and almost to 1, which would be a perfect classification score, F1 score. But the brown values are the F1 scores for classifying sea floor. And you can see here that there's a variable in this location. Each algorithm performs differently based on those variation of values. But the ensemble, the column in the middle, shows the highest F1 score for classifying sea surface. And like I said, the ensemble is created to perform at least as well as the highest performing base algorithm. Another key benefit to this ensemble, which is an XG boost, is that it can look at its decision trees and create a probability of classification correctness, if you will. And that's what we've turned into a confidence score. This is a really good visualization, and then I'll get to the confidence score of the comparisons of classifications of the base algorithms. So you can see here the top is manually labeled reference data. So this is what we say is the, quote, ground truth of sea surface and sea floor for this particular profile. Then each profile moving down from the manually labeled reference data is the output. So the top one is the ensemble. And you can see as you go through, we have the 6 input I think we just have 5 because I couldn't fit it on the slide, but you can see the variation. Like if you look at the Bathy Pathfinder algorithm, that over here toward the right, it gets a little confused and grabs some of the water column and labels it as bathymetry. Whereas maybe if we skip down to the median filter, which is second from the bottom profile, you can see that for whatever reason, that algorithm misses some of those bathymetry points on the right. So each of these algorithms has a different type of error associated with it or capability in correctly signal finding, but we can use all of them in the ensemble to create the best guess of classification. So the confidence, as I mentioned, is an output of the XGBoost ensemble, and it's kind of internally generated, but it has a lot of variables, and it's also based on this current composition of base algorithms. So what I want to emphasize here is that right now for version 1, release 1, we feel that the confidence level of 0.6 or higher is a good way to users can filter the data for high confidence classifications. However, that's based on the input algorithms, as I said, and so next versions might have a different threshold recommended of confidence. So be mindful of that as you look to version 1 release 2 and version 2 that comes out probably next year, that those confidence thresholds or filtering might change. This shows you those seafloor classification photon classifications from about 0.6 to 0.1. And you can see it is just by visually inspecting that it seems pretty accurate, and there's very few outliers in terms of what the ensemble is predicting. So in terms of the full ATL24 workflow, I have a version here. So let's start in the upper left box that shows the intersection of the ATL03 granules and then our ATL24 search mask. The search mask is a global mask that uses a derived retrievability score for probable ISAT2 bathymetry detection. And this is based on water turbidity and maximum depth of a given region. And then we take that mask and we widen vertically and horizontally to ensure that we don't miss anything. And the mask guides the processing of ATL24 to just our coastline nearshore environments. So moving down along the left side, we process the data and use a function we created called CoastNet to make a first pass at identifying water surface photons. This is because we have these 6 independent algorithms for classifying bathymetry photons, but some of them need a starting point of where the water surface is. And that's why we do a first approach to water surface classification. Each of these algorithms use a different approach to signal finding. Some of them are histogramming approach or density evaluations. Some of them are machine learning approaches. But again, all of these predictions from these base algorithms are fed into the ensemble. Once the ensemble provides the classification predictions, again, which is supposed to be the greater than the sum of the parts, we perform some blunder detection and outlier removal, which are, if we go down the gray boxes in the middle of the flow chart. And then we do a final sea surface finding and provide a correction for the index of refraction of water for any of the photons that occur beneath the sea surface. The uncertainty calculation is calculated from a subaqueous uncertainty lookup table, which is the kind of parallelogram at the bottom, and then it also uses the coefficient of diffusion, the diffuse coefficient, from VIIRS, the KD490 value. So then that's our uncertainty value on per point level. And then our data product is generated with a variety of parameters. Some of them are listed here on the far right. Seafloor ellipsoid height, seafloor orthometric height, and uncertainty estimates along with the confidence value. And I should also mention for the refraction correction, as you can see up in this top parallelogram, we do have our own refractive index layer that's created from global level temperature and salinity values to create the most accurate correction in time and space. So we kicked off the full production of ATL24 back in February. It took about 13 days to produce 27.6 terabytes of data. We processed this in AWS. I thought these metrics were pretty interesting to say that a total linear coverage of bathymetry was 13.7 million kilometers. And then you can see here the number of our bathymetry points, which we do follow the ASPRS convention of classification. So our bathymetry is class 40 and our sea surface is class 41. We collected a little over 7 billion bathymetry points. And if we just filtered those by our confidence value of 0.6, then we had more than half identified as high confidence bathymetry. And you can see here in the figure the coverage in yellow of where we have bathymetry within the product. We chose 8 sites that we had pretty consistent reference data to compare to understand how accurate, not the classification confidences, but how accurate the actual bathymetry elevations were. And you can see here, this is on the left column are the accuracy test results for all of bathymetry points at those 8 sites. And you can say we have an RMSE of 0.68 meters. And then if we threshold those values for high confidence on the right plots showing a reduction in RMSE of down to 43 centimeters. And so it does improve the overall quality of bathymetry elevations by just using high confidence, but you also have to weigh the impact of removing some of those bathymetry points that could very well be bathymetry, but not all of the algorithms predictions supported that. One of the things that is, I'm sure, would be interesting are some strengths and limitations to the current version of ATL24. And I just want to emphasize that the ATL24 is a global coverage of the Earth's coastlines, and we have yet to have a space-based laser bathymetry system that provides the wealth of data that ISAT2 is providing. I think our approach for signal finding and classification is pretty robust because it can leverage the advantage of each individual algorithm or base algorithm where it works well, and we don't lose any quality of the output data and signal finding. It's accessible in a variety of ways. You can download the data from several methods, which sure is part of this training. The architecture of the algorithm is also configured for continual improvement, meaning that we can, right now we have 6 base algorithms, but we could up that to 24 base algorithms, and it's all set up, the structure is set up to continue to add algorithms as methods are identified and implemented. And then also the accuracy of this product is pretty great, and it has been proven suitable for calibration and validation of spectral satellite-derived bathymetry in most cases. Some of the limitations, though, I can mention here are that some of the conditions do result in variable data quality, as you can imagine. And then the current uncertainty estimates are overly optimistic, but we're still working on refining that and making them a little bit more realistic. The data exists only on the coastlines and coincident with the current search mask. So the ATL24 algorithm is not run anywhere except the intersection of the ATL3 granules and the search mask. And then the photon classification conflicts between ATL24 sea surface and ATL08 terrain surface do exist. So if you are interested in seamless, topo-bathy profiles along our coastlines and you pull in ATL08 terrain heights, there's some confliction in the photon classification. So there's not that continuity yet in those two along track products. And I wanted to point out a few resources that might be helpful in using ATL24 or understanding more about ATL24. The first two bullets are papers that were recently published this year in Earth and Space Science. The first one, Parrish et al., it provides more detail about the accuracy analysis, those 8 sites that I was showing earlier. And then the second one, Magruder et al. is an in-depth description of the base algorithms and the ensemble, and talks a little bit more about the metrics associated with understanding the performance of the classification. And then the algorithm theoretical basis document is the last bullet, and that gives you even more information about the algorithm. It includes the refraction correction approach. It also includes uncertainty evaluation and all of the other details about the product. And I think that's all I have. I'm so happy to be here today with you, and I will throw it back over to Sean.
Thank you, Lori, for the excellent overview of ISAT2 and the ATL24 Bathymetry product. We will now transition to Diane Fritz from the National Snow and Ice Data Center to present on ATL24 data resources and access. Diane, over to you.
Hi, I'm Diane, and I work at the National Snow and Ice Data Center, or NSIDC. And I am going to do a quick segment to show you ATL24 data, that bathymetry product, and the resources and access that we have for you at the DAC, or Distributive Active Archive Center. So what is the role of NSIDC? We preserve many, many data sets, including all of the products from ISAT2. Although we are the National Snow and Ice Data Center focused on the cryosphere, you'll notice from Professor Magruder's previous video that she showed, ISAT2 is a global data set, all of the ones that get derived from that mission. And so we have all of those products at NSIDC. We have a lot of products from other satellite missions, airborne surveys, field observations, all sorts of different things related to the cryosphere. And we are one of 11 DACs, and you can see on the map here where some of those are located. We are in Boulder, Colorado, but we are accessible all over the globe by emailing us at nsidc@nsidc.org. Data is free for anyone. You just need an Earth data login to be able to access it, but it's free to create that as well. And it's helpful to be able to work with GeoTIFFs, NetCDF, HDF files, other kinds of science files like that. But we have user guides also to help you. And my job in the User Services Office at NSIDC is to help anybody use the data that we host at the DAC. So this is an example of one of our dataset landing pages. In particular, this is the ATL24 Bathymetry product landing page. And I just want to show you some useful things that if you go here, you'll be able to find a user guide that talks a little bit more about what the data is. We have a citation, so you can easily give credit to the people that produced this data, but also know who they are and be able to look up the papers and other research that they've done. And we also have a subscribe possibility here. So if you want to know more about a particular data set, you can sign up for email updates of that data. So if there is an update, something that is a new parameter or something like that that gets added to a new version, you can get a notification about that. But on our dataset landing pages, in addition to these icons at the top, we also have a menu for being able to find things on the side, that right menu that you see there. So this gives you access tools, documentation, and help articles. What I have on this screen right here is an example of two different access tools that we have for ATL24. One is the NASA Earth Data Search, which I'm going to do a quick little demo of how you can use that to find ATL24 data and actually subset it. There's also SlideRule Earth as one of the tools, and many more, and you'll get to hear more about SlideRule Earth later. We also have documentation, these technical documents, if you want to dive further into the algorithms that were created to get the bathymetry product out, data dictionaries and user guides. And then we also have help articles that are going to help you maybe just understand how to work with a certain kind of platform with HDF files, for example, or know a little bit more about the data. So all of these resources are available from that dataset landing page. Now, if I go to the tool, NASA Earth Data Search, I will see some kind of visualization like this, and I'll demonstrate this. You can search for data by mission. So I can put in ISAT2 and see what's available. I can look for keywords. If I know the data set short name, ATL24, I can put that in and look for it. So this is a way to access data from all of the NASA DACs, not just NSIDC. There are customization services for select data sets in here as well. And so I'm going to show you what it's like to just pull a small spatial chunk of an ATL24 file and visualize that. So this is a picture of Panoply. It is a nice kind of visual browse platform, and it does some more things as well, but NASA developed this, and it's a really nice way to quickly look at a ATL24 granule and see what is available in it. As Professor Magruder mentioned, there are classes of photon classifications in this data set, and that variable is class_pH for photon. And 40 represents a bathymetry photon, and 41 represents those sea surface photons. So on the left here in the small side, I've got a full granule download, and I've zoomed in and changed the scale so that 40, the bathymetry photons, show up in yellow. And you can see that in here that we have some pretty good returns in the area of the Bahamas for bathymetry. So I'm going to show a little demo using NASA Earth Data Search to grab one of these ATL24 granules near the Bahamas and show you what it's like when we open it in Panoply. So I'm going to dive over to my browser now, and this is the dataset landing page for ATL24. The URL is nsidc.org/data/ATL24. You don't have to type in the rest. The version will self-populate. But if I scroll down, you'll see a map that shows that the ATL24 coverage is global. And you'll see these different data access tools that you can get. SlideRules down there. We're going to go to NASA Earth Data Search and click on this. And it's going to take us to a page already with ATL24 loaded into this. Now I can hover over these different granules. I'm going to click on this one, and it'll take me to a place where this one exists. So this is that one that I showed on the slide deck. I can do spatial search here. I can also do temporal search with these controls. I'm going to just draw a little box and grab a little bit of this granule in this upper part. But in doing that spatial search constraint, I still have all of these other granules here as well. So you can see that I still have 212 that go through this over the course of the mission. For the purpose of this demo, I am just going to copy this granule name and search by it as well and reduce it down to 1. But you can use wildcards in here, or you can do a temporal search to narrow it down a little bit more. So with this, I'm going to say I want to download all, which is down to my 1 granule at this point. And it's going to take me to this platform where it's going to give me an option to say, do you want to just download this data straight, or do you want to customize it? And Harmony is the tool that we have for doing spatial and temporal subsetting on some ISAT2 data sets. So I'm going to choose a service. The only option here for this data set is the Harmony trajectory subsetter. And once I've selected that, I can scroll down and see that had I had more data sets or a temporal constraint, I could use that, but I still have just that 1 granule. So I have my spatial subsetting here. That looks good to me. I'm going to click Done, go to click Download Data, and it's going to start putting in that order for me with that, taking that bounding box and actually trimming my granule just to that area. I can go to my order status and see how Harmony is doing. And it looks like that job, it's going to look at that job code. It was already successful. This takes a little bit of a lag time to show that, but that's where you can go and get that link directly. It can also notify you when everything is finished processing, and you can pull data from here. So I'm going to hop over to Panoply. I've already downloaded a subsetted file before this, and this is what it looks like when you open that. And you can see the 3 beams here. And when I expand one of those from this is the ATL24 product, and we have our class of photons, we have heights of different kinds and flags and different kinds of information. And then I can plot these. And if I'm looking at my class of photons, and again, I've changed my scale here in Panoply from 0 to 41 to 39 to 41, just so I can see that bathymetry photons in the side. So I can see that I've got some good response there. I can also bring up the height data as well. And so if you recall the way that I grabbed that data, there was a little bit of an island going across here, and you can see some of that height shown in this area. So that's how Panoply can help you inspect these HDF files pretty quickly. I'm going back to our data order and see that it's here. I can actually click on this link and get this subsetted file directly downloaded from clicking here. But if I have a lot more granules in here, I can use this Earth data download, and it can pull everything in one download for me. This is a different software you need to put on your computer to have that work, but it's really quite simple, and we are happy to help out with that. So I have one more slide to show, and that's just some resources that I've provided. This is a link to the ATL24 dataset landing page, a way to get the Earth data login for NASA data in case you don't have that already. Here's a direct link to NASA's Earth data search for all the DACs, the Panoply software from NASA, and We have some help articles, the Earth Data Search Guide. This will tell you how to use Harmony subsetting a little bit, but we also have Harmony in as an API as well. And there is a Python library called HarmonyPy that you can use as well if you're doing programmatic subsetting in a Python notebook, for example. And then here's also a link to SlideRule Earth, but other people will be talking about that. So I hope this helped you get a good orientation to resources that we have for supporting ATL24. And in the User Services Office, we are here to help you. So feel free to email us at nsidc@nsidc.org.
Thank you, Diane. Next, we'll hear from JP Swinsky, who will present on the SlideRule web service for plotting and downloading ATL24 data. JP, over to you.
Okay, thanks for that introduction. I'm going to be talking about SlideRule Earth, which is a collaboration between NASA Goddard and University of Washington. So what is SlideRule? SlideRule is a public web service that has REST-like APIs for processing science data. The goal is to provide researchers with low latency access to on-demand data products. And we provide those data products using parameters supplied at the time of the request. So it's like a real-time data access system. The entire system runs in Amazon Web Services US West 2, and we have access, very efficient access to all of NASA's Earth data products stored in US West 2, like ISAT-2, JEDI, Landsat, and a growing list of others. As a team, we support multiple clients for accessing SlideRule. The two main clients are our Python web client and our Python client and our web client, which I'll be talking about today. But we also support Node.js, and for those power users, you can access our system with curl. Here's on the screen, you see just a cartoon of what the system looks like at a very high level. The users typically interact with SlideRule using either a Jupyter Notebook or their web browser if they're using the web client. We run a bunch of servers under the domain SlideRuleEarth.io. And then behind those servers, we have access to things like NASA's Common Metadata Repository, which is their index for the NASA's Earth data products, as well as the Earth Data Cloud that I mentioned before. You can find us, more information about us on our website, which is SlideRuleEarth.io. You can point your browser to that. You're always free to contact me. I have my contact information there. And for developers, please look us up on GitHub. We're completely open source under a BSD 3-clause license. So why did we create SlideRule? So the idea is that we're hopefully improving the way data is accessed in the cloud. So here's just a picture of what it's like to access data in the cloud without a service. So here you have different S3 buckets holding different data products like the ATL03 data from ISAT-2, the JEDI data, the Blue Topo data, the harmonized Landsat Sentinel data. And it immediately becomes evident that if you're working from a single Jupyter Hub instance or your laptop, it is very challenging to work with these data sets at a global scale. There's just too much data to work with. You also need to know the format of all these different data sets. For instance, if you're trying to correlate ATL06 ice surfaces to the Arctic DEM, you need to be able to figure out how to get the acquisition date from the Arctic DEM rasters. And that's going to be different than the way you're going to get an acquisition date from HLS, and different than it's going to be from Blue Topo and so forth. And then lastly, there's going to be common operations that you're going to want to do on the data that are going to be very compute intensive. For instance, if you're working with a photon cloud, like we are with ATL24, it is very compute intensive to take that photon cloud and resolve it to a single elevation over a certain aggregated area. So that is why we came up with SlideRule as a service for accessing this data. We provide optimized direct access to the raw data. So if you want to just read ATL24 or Blue Topo, you can use our services, and we will very efficiently in a parallel way read the data as fast as possible and give it to you directly. But we also supply efficient subsetting services. So if you want to take the ATL24 data and look at it just in an area of interest, you can provide that polygon to SlideRule, and it will go out and it'll pull all the different granules and in a parallel way provide them to you in one single response. And then we do on-demand processing right next to the data. So we are running in US West 2 right next to the buckets that are stored in that same data center. And we can produce customized data products on demand using parameters supplied by your request. So that's in a nutshell what SlideRule is. And now I'm going to transition to talk about, to give a demonstration of our web client. So this is pretty new. It just came out this year, and this is one of the ways, maybe the easiest way to accessing SlideRule, which is doing so from your web browser. So this is the web client. You can get to it going to client.slideruleearth.io. You can also find links to it. You can also find links to it from our main web page. So when you navigate to the web client, this is the screen that you'll see. And the first thing you're going to want to do for accessing the ATL24 coastal bathymetry data is you're going to want to go over here and select the ISAT2 coastal bathymetry selection box. What that does is that puts a search mask overlays it onto the map, showing you where there's data available. So everything that you want to do should be within that search mask so that you're sure to get a response back from our service. So I went and did a little poking around, and I found a spot that has some good bathymetry off of the coast of Cuba. So I just searched for it, and it zoomed me in there, and I know that there's some good bathymetry in this area here. So what I'm going to do with the ISAT2 coastal bathymetry box selected is I'm going to take the box tool, and I'm going to draw just a bounding box over this area. And you can see that it automatically shows you the size of the area. For requests using our public service for ATL24, we ask that it be underneath less than 1,000 square kilometers. So 550 some square kilometers is just fine. And you can see what it is if you hover over it. Once you have the bounding box, you can just click Run SlideRule, and it will generate that request for you, send that request to the servers running in US West 2. Those servers will subset all of the data that needs to be subsetted, collect it all in a single response, and send it back to the browser that you're running. Once the data is all loaded, it'll pop up this analysis screen on your browser. The first couple times through, you're going to get a lot of helpful advice. I think it's after 5 requests, we figure that you've read all the helpful advice and you'll no longer see those. If you ever want to reset or get it back, you can always reset the system here and you'll go back to being like a new user. So now we have a display of all the different tracks. You can hover over it to see the information of the different photons returned. These are all the bathymetry photons in that bounding box in ATL24. So you can hover over, you can see the confidence level, the orthometric height, the reference ground track, things like that. You can select the different tracks, and on the right, you'll see a plot of the along track photon cloud, just the bathymetry photons. So I'll just show a couple different ones and see what you can see what they look like. That's a neat one. Okay, let's choose that, or maybe choose this one here. Let's choose this one here. It goes down to 5 meter depth. So now this shows me a zoomed in view of the bathymetry, but I want to get a better context, but I want to look at the whole photon cloud that it comes from. So if I click this, show photon cloud, it actually goes out and makes another request to the server to grab the ATL03 raw photon cloud and combine it with the ATL24 photon classifications. And then it gives us now this full view of the data. So what we're looking at now is the input data, if you will, to the ATL24 algorithms that produce the classifications that we saw on the previous plot. And so if we zoom, let's zoom in here. So I just zoomed into a section. You can see the white here is our sea surface. That's the sea surface classified photons. The purple are the unclassified photons. The ATL24 algorithm is just saying it's neither sea surface nor bathymetry. And then the green is the photons that the algorithm identified as a bathymetric return. Okay. I think one other thing I'll show here is, let's go back to this, is sometimes it's useful to just get a quick view of what the whole data set looks like. And so we do, for that, we do provide a 3D view of it. And so this here is showing what the whole data set looks like. And you can see there's some sea floor here at the bottom there. I guess also you have a lot of things at your disposal as far as controlling what the plot looks like. So here we are coloring the points based on the orthometric height. If we wanted to color them based on their confidence level, this is now the same plot, but it's showing which photons have a very high confidence in the algorithm of being a bathymetric return versus ones that have a low confidence. So you can see up here we have some really high confident ones, and then right here, appropriately so, it's a little bit less confident. Lastly, I will just say there is, for those that are power users, you can see what the actual request to the server looked like here. Okay, so this flow has so far been just a very simple, straightforward flow of getting access to the ATL24 data. We do have in the web client some options for some more advanced access. So now go over here, go back to the request, and go up here to this selection button and choose advanced. So now we see we're selecting the ATL24X API, and this is going to give us access to more features that the server exposes. Specifically, I'm going to go now to this ATL24X fields. Before I do that, I'll draw a bounding box, and I'm going to make this a much smaller bounding box because we're going to get some more data. You'll see why. Okay. So I'm going to go here, and now in my request of ATL24, instead of saying, I don't just want the bathymetry, I want all of it, the unclassified and the sea surface, similar to what we saw when we did the ATL03 request and used the ATL24 as a classification. And then also, I don't want just the main fields. I want all of the fields that are in the data product. So here, I'm just going to select whether or not this compact selector, and I'm going to leave it off now because I don't want the compact version, which happens to be the default version when we do just a general request. If you wanted to, you could also do some filters here, like you could filter on the confidence threshold, you could filter on the turbidity and whether or not there was valid turbidity or wind speed, and whether or not it was at night and the sensor depth was exceeded. You could also even pull in some ancillary fields from the data product. But we'll leave it just like this, and we'll show the request parameters, and you're going to see now we've got some additional parameters in our request. And we'll make this request. So this is, again, a smaller area because my guess is it's going to pull in a lot more data because we're asking for all the photons and not just some of the photons, not just the bathymetry photons. Yeah, look at that. So you can see this just in this really small area, and we would just caution, if you want all of the photons beyond just the bathymetry photons, you do want a small area, not just for the load on our servers, but it can very easily overwhelm a typical client laptop running this in your browser as well. So this very small request had 709,000 photons returned. But you can see this is a plot here. And then we can do things like, now instead of doing orthometric height, let's do the photon classification. And you can see that over here we have these higher classifications, which is sea surface and bathymetry. So right away I can look at this and I can say, oh, over here's land, and over here is your sea surface and bathymetry. And if that wasn't super clear just by looking at it here, I'm going to keep my pointer here, and I want you to look over at the left side of the screen where you see the geographic map. And you should see a moving target showing which photon you're highlighting on the map corresponding to this elevation plot on the right. And that just confirms that, yeah, this is what you're looking at here is land, and what you're looking at here is the water. Now, what you can do when you get all of the data is you can export it if you want. So we can go to our table and this table tab, and now we can run an SQL query against the data, and we can get a full, now all of the raw data is being shown. Well, actually just the first 1,000. So you can, if this is more for power users, but it gives you full access to all of the data that you're looking at. I should note right now that this entire application, everything you're seeing here, is running in the client. So this is a browser-side, client-side application, single-page application. All of the querying, all of it is done on your computer, so you own the data. This is not being stored on the server anywhere, and so we're just giving you tools to be able to interact with the data that is being returned by the server. So you make the request to the server using this client, the server returns the data, and then you own that data and can interact with it how you please. And if you build a query that you really like, you can export the CVS to your computer. Or if you want to just export the raw data that came back from the server, you can go over here and choose either GeoParquet or CSV as the format to export. Coming soon is LAS. That should be out probably mid-December. We support it on the server side, and very soon we're going to tie it in on the client side as well. Okay, I think with that, I'm done.
What a great demo on the use of SlideRule web service for accessing and plotting ATL24 data. Thank you, JP. The following summarize the concepts covered in part 1 of the webinar series. NASA's ISAT-2 carries a photon counting laser altimeter, which is named ATLAS. ATLAS provides near contiguous, along track sampling using 6 individual beams of green light at 532 nanometer wavelength, providing high vertical resolution. Every photon detected by ATLAS has a latitude, longitude, and elevation associated with it. ATLAS provides surface-specific data products developed by experts and include products for land ice, sea ice, the atmosphere, vegetation and land, oceans, and inland water. ATL24 product provides ATLAS-derived coastal bathymetry via ensemble machine learning models, where each photon classified as bathymetry will have a confidence value assigned. The National Snow and Ice Data Center, or NSIDC, provides access to ATL24 data, metadata, and tools. NASA's Earth Data Search is used to find and spatially subset ATL24 bathymetry data. SlideRule is a public web service with low latency access to on-demand data products stored in S3. And SlideRule provides on-demand processing next to the data for generating customized data products using parameters supplied in the user's request. Looking ahead to part 2 of the webinar series, we will be covering the following topics: how to generate satellite-derived bathymetry using methodologies combining ATL24 bathymetry with optical satellite data from Sentinel-2, Python workflows for filtering, visualizing, and analyzing bathymetric point clouds, integration of ATL24 into existing NOAA workflows for nautical charting and coastal zone management, an overview of NOAA's SatBathy tool and its capabilities for automated satellite-derived bathymetry generation using ATL24. Before we transition to the question and answer session, I want to remind you there will be one homework assignment which you will be able to access from the training page on December 4th. Answers must be submitted by Google Form with a due date of December 31st. To receive a certificate of completion, you must attend all 3 live webinars and complete the homework assignment by the deadline. You will receive a certificate via email approximately 2 months after completion of the course. We want to thank once more Dr. Lori Magruder from the University of Texas at Austin, Dr. Diane Fritz from the National Snow and Ice Data Center, and J.P. Swinsky from NASA Goddard Space Flight Center for their presentations and instructive demos. Below is the contact information for Lori, Diane, and JP, along with links to the ARSET website and social media. If you enjoyed today's webinar, we hope you will sign up on the ARSET listserv to receive notifications of future trainings and follow us on social media for future relevant announcements pertaining to NASA's Earth sciences. Below are a list of resources relevant to the material covered in Part 1 of the training. We will now transition to the question and answer portion of today's training.
Great, and thank you for everybody that's been submitting your questions. We've gotten a lot of good ones so far. So jumping right into it, question number 1, can we develop watershed models using the data from the ISAT-2 imagery? What would be the minimum resolution?
I'll go ahead and take that. I'm not 100% sure about the kind of model that is wanting to be developed, but I think hopefully the presentation was good at describing the data format. So we have a long track photon returns, and those tracks, we have 6 beams that are come in 3 pairs, and the pairs are 90 meters apart from each other with 3 kilometers separating each beam pair. But the long track resolution is quite good at around 70 centimeters. And so it's really the elevation data that you get from ISAT-2, regardless of which product that you're looking at, is really good validation data along that track. So I hope that helps answer that question.
Okay, Diane, thank you. Question number 2, can we derive data for different time periods to do comparisons? It would be useful for seabed mobility assessments.
This was me as well. So ATL24, as many of the other data products, are derived from the main ATL03 photons, and those have been gathered since 2018, and you can separate out those files with temporal queries and pick what you're looking at different time periods. Of course, the return time of the ISAT-2 satellite is 91 days. So between that and getting good data at your particular location may limit some of what you're trying to do with those comparisons, but those are the parameters for it.
Awesome. Thank you, Diane. Question 3. is the ATL24 product already corrected for tides, or is this a post-processing step we have to consider, especially for locations where tidal range is considerably wide?
This is Chris. I'm a speaker on the Thursday session, but I can answer this if nobody else wants to jump in. We actually don't need an explicit tide correction step in the ATL24 workflow because we use a process similar to what's called ellipsoidally reference surveying in the hydro surveying world. Basically, it means that our data, our heights or our depths are not based on the instantaneous water surface. They're relative to a vertical datum at every step in the process, either an orthometric datum or an ellipsoidal datum. And for people that want to transform to a tidal datum, like mean low or low water, in the US at least, we can use a tool called NOAA's VDatum to be able to do vertical datum transformations. So basically, we don't actually need an explicit tide step, but we leave it to the user to be able to transform to different vertical datums, including tidal datums, if they want to do so.
Great, Chris. Thank you so much. Question number 4. That's a very clear scatter plot. Could you tell me about the steps taken to check for overfitting?
I can answer that if no one else is. This is Jeff Perry. I'm on UT's ATL24 team. And I kind of wrote this, assuming I understood the question correctly. I don't actually have the plot in front of me, but the individual I should have wrote this first. The individual algorithms may or may not overfit depending on their nature. They're all different, right? They all are very different algorithms. The final model, the ensemble, we use XGBoost just because it's fast for no other reason. It is prone to overfitting. We can fix that by adjusting the hyperparameters of the model. But after all is said and done, a lot of the overfitting we correct by applying this blunder detection that's like, really obvious errors that some of the models can make. Like some of them can put bathymetry on top of sea surface, and obviously you can't have that. So that fixes a lot of those overfitting errors. I hope I answered that sufficiently.
Great, Jeff. Thank you so much. Really appreciate that. Question number 5.
You're welcome.
How much work will it take to extend this approach to inland waters? Is it possible, and is any team working on such a product? What about in northern latitude lakes and ponds?
This is Chris again. I can answer this one if no one else wants to. In developing ATL24, we very purposefully did not consider inland waters because there's already a dedicated data product for inland waters, which is ATL13. And ATL13 does also include a bathymetry attribute.
Terrific. Thank you so much, Chris. And hopefully whoever asked that question can go and search for that ATL13 product. Question 6. What applicability does this data have for bathymetry mapping of inland and near coastal lakes?
Is that that one seemed like similar to the previous question, right? Inland waters, again, that's ATL13 is inland waters.
Okay, great. Thank you, Chris. Question number 7. Are positive depth biases in ATL24 common, and what could be the cause?
I can maybe take that one too, unless Jeff or somebody else wants to go ahead. I think that's still to be determined. I think that's a great case where we'd like to hear from users of the data as they do comparisons against independent reference data, if they're seeing positive depth biases. In that accuracy test that was in Lori Magruder's presentation, we actually didn't see a bias being consistently in one direction or another. I think we saw biases of around 10 centimeters that could either be positive or negative. There are some reasons why we might expect a bias. For example, one of the things that our ATL24 team has started talking about recently is what's known as forward scattering bias in bathymetric LiDAR. But I think we just haven't, part of the importance of ATL24 and of ISAT2 bathymetry in general is that there's just so many areas in the world where we don't have really good existing bathymetry. And so that's kind of a double-edged sword. It makes the data products quite valuable, but it also means that there's, in many places in the world, not a lot of existing data to compare to.
Okay, great. Chris, thank you so much. Question number 8. Does the SlideRule web client apply any denoising or classification algorithms before presenting ATL24 bathymetry points? Or are we viewing the raw ATL24 photon returns?
This is JP. What was shown when we show it through accessing it through the web client, it's just the raw bathymetry. In the general tab, we do by default filter any low confidence bathymetry just to keep the requests as fast as possible, but then allow the user to drill down and raise the threshold if they want. Now, in a couple of days, there's other APIs where you can apply different processing steps to the data being returned. Those steps aren't available in the web client, but are available through the Python client. Also, I guess just going back a couple questions, for those interested in ATL13, the inland bodies of water, there is also, SlideRule also supports accessing that data from the web browser as well. Instead of the coastal bathymetry tab, you just select the inland bodies of water tab and you'll get the ATL13 data product.
Great. JP, thanks so much. Question number 9. How does ISAT2 distinguish between photon returns from the sea surface and photon returns from the sea floor in shallow coastal waters, especially considering issues like photon noise and surface wave variability?
This is Jeff again. Matt had answered this, but he's having technical difficulties. Otherwise, he would probably be speaking up. But as you can see in his answer there, sorry, now I'm just kind of reading it. But the question is, how does it distinguish between photon returns and shallow coastal waters? I mean, we, like he says, we train on a lot and a lot of data, and sometimes in really, high waves, we do make mistakes, and the trough of a wave can be classified as seafloor. In release, we've had, so what we've been calling version 1 of the algorithms, we've had 2 releases of this, and the second release fixes a lot of those. It goes back and looks especially for those places where this trough of the wave is misclassified as bathymetry and fixes them. So that's one way we deal with that.
Okay, Jeff, thank you so much for chiming in, and we apologize that Matt is not able to access or unmute himself. But moving on, question number 10: how does the ATL24 handle the challenge of separating true seafloor returns from water column backscatter in shallow coastal zones where turbidity is high?
Hi, it's Jeff again. So, I mean, obviously, if there's too much turbidity and the signal disappears, there's nothing you can do. At some point that's going to happen, right? And if the noise is too high, well, there's, if you lose the signal, you lose the signal. Again, we have an ensemble here, multiple algorithms. And so, for example, the algorithm CoastNet, it operates on high, imagery with high vertical resolution. You can very clearly separate the 2 signals if there's not too much turbidity. And so it separates those out. And again, as we keep saying, the ensemble has an opportunity, if some algorithm misses it or confuses the 2 signals or makes assumptions about the signal, like I mentioned in the beginning, some algorithms won't even predict bathymetry if the bathymetry signal is stronger than the sea surface. But the ensemble and the blunder detection has a chance to go back and fix all that. It doesn't always fix it, but it has that opportunity.
Great, Jeff, thank you so much. Question number 11: is bathymetry available for large river systems like the Mississippi River, or are there too many issues with turbidity or orbital path shoreline geometry?
I think that's again similar to the previous questions on inland waters, where that would be the ATL13 product and not ATL24, which is coastal focused.
All right, Chris, thank you. Question 12. In SlideRule, is the data derived per line only, so the spatial variability is poor?
Yeah, so I think what you're asking is all of the data products right now that we generate or provide services for along track, and they are, we would love to have produce image data, raster data sets. We hope to in the future, but right now we're funded only to support the along track products.
All right, thanks, JP. Question 13. Does the Python library allow for larger bounding boxes?
So this is just limited by the retrieval of the granules from the cloud-hosted data. So you can make larger bounding boxes, but your code may stall a little bit. But I put in a reference here for being able to look up Harmony and look into the Harmony Pi library and see. So to be honest, I haven't done a very large grab myself, so I don't feel 100% confidence about this answer.
And for SlideRule, it's really easy, and I'm guessing the Harmony would have the same fundamental problem. It's really easy when you're looking at a globe to not realize how big of a request you're making. I don't know if you remember when I was drawing that really small box in the demo, and that had 700,000 points in it. You can imagine a factor of 100, a factor of 1,000 on that. Easily, you're easily talking a billion rows, and so with these photon cloud data sets, it's very easy to get huge returns. So all that being said, on SlideRule, we let you do it, and we'll do the best we can, but it's typically the client crashes before the servers do. That's just what we notice.
Yeah. So as JP is saying, these data sets are massive. So really kind of doing some pre-look of, what is your temporal subset that you might want, or your spatial subset, and really restricting it to what you truly need is the best way.
Yeah.
Great. Thank you, Diane and JP. Question 14. Is turbidity the main thing affecting the confidence level? Does that come from veers?
I'm not sure who put this answer in, so I can answer if no one else is. Yes, the answer to the first question is yes. Turbidity and background noise is what's affecting the confidence level, but it's implicit. It's not. We don't measure the turbidity and then measure the background noise and then make assumptions, make predictions based upon that. It's just implicit in most of the algorithms. When there's more turbidity and more background noise, it's just going to have a harder time deciding what the label, what classification of photon is. And so then down in the answer, the XGBoost model, it's a tree-based model, and so it uses that tree structure to determine what the confidence level is. It's like a probability. It's a softmax, if you know what that is, but it's not, strictly speaking, it's not a probability, but it looks like a probability and acts like a probability. So that's where that comes from. Is it's part of the decision tree model. Will for every photon assign probabilities or softmax probabilities to each label and then choose the most probable one.
Thank you, Jeff. Question 15. Can we use it for detecting plate movement of tidal areas to get information about upcoming earthquakes?
I'm just going to unmute and say that this is a really interesting application idea. Chris, if you please comment, but I think that this is beyond the production of ATL24 data, but it's great to have people thinking this way and thinking about applications for this data.
I was going to say the exact same thing. It's really interesting, but beyond the scope of what we've looked at. I don't know if the spatial resolution and accuracy support that. Yeah, if anybody looks into that, I'd be very curious to hear what they find.
Diane and Chris, thank you. Question 16, I think, has been addressed in previous questions. So for those that are interested in inland bathymetry, definitely check out the ATL13 product. Question 17, in satellite-derived bathymetry, workflows that use ATL24 as reference data for training models on Sentinel-2 imagery, are turbidity and bottom type limitations generally encountered first in the multispectral reflectance rather than in the ATL24 LiDAR signal?
I was just reading this question. Oh, somebody scrolled, and I'm not sure which one was this again. Oh, 17. In the Thursday sessions this week, in the presentations that both I give and Gretchen Imahori from NOAA, we're gonna talk about using ATL24 in combination with satellite-derived bathymetry from multispectral imagery. So hopefully those presentations will help answer this. Let me read this question again, though. Are turbidity and bottom type limitations generally encountered first in the multispectral reflectance? They're sort of independent workflows, but some of the constraints are the same. So obviously, in any method of satellite-derived bathymetry, relying on spectral data and relying on having returns from the seafloor, turbidity is one of the main limiting factors, and that's the case also with ISAT-2 bathymetry. Generally, the ranges in which they both work are pretty similar, which makes ATL24 a pretty good choice for calibration and validation, or just integration with spectrally derived bathymetry. I hope that answers the question, and I hope that the talks that Gretchen and I give on Thursday will also help answer that.
Great, Chris, thank you so much. Question 18, are there tools available for accessing the ATL13 products such as SlideRule? And Diane, thank you so much for adding this link so that they can access that data set. Question 19, is there a gridded product available or planned for the future for the US East-West? It's covered by coasts. Thank you.
I don't think our team has explicitly talked about doing a gridded product. From the beginning, the intent was for ATL24 to be in a long track product. I think that certainly there are tools and options that will help end users create gridded products. In some areas, I think we're just starting to see enough coverage from all of the different ISAT-2 overpasses that we maybe have enough data in places to do like a gridded bathymetric DEM solely from ISAT-2 data. But in other areas where people want a gridded product, kind of like wall-to-wall coverage, those are cases where the integration with spectrally derived bathymetry from multispectral imagery can be very valuable.
Great, thank you, Chris. Question 20, what changes are expected to the confidence levels next year? It looks like Matt might have answered this one, and unfortunately, Matt does not have access to this WebEx, but he did provide an answer, which I will read, but I apologize because I'm not the one that contributed this answer, but we are actively improving the constituent models and investigating new models to add into the mix. The confidence levels are entirely dependent on capabilities of the constituent models. After building the ensemble and prior to publishing the next version of ATL24, we will conduct a study of confidence values relative to reference bathymetry datasets to determine the updated best practice value to use. Thank you, Matt, for adding that and for answering that question. Question number 21, how critical is VIIRS KD490 to the uncertainty assessment? I would think clouds and land adjacency would greatly reduce the quantity of KD490 retrievals, and quality of these retrievals would be reduced in optically shallow waters unless alterations to the standard KD490 algorithm are used to minimize benthic contamination.
I'm not sure who typed that answer, but I agree with what's given there's the answer. The VIIRS KD490 is not directly used in the depth retrieval. It is the only place where that's currently used is in the uncertainty calculation. And as it says in the answer there, that's used in data that goes into the uncertainty lookup tables. Yeah, hopefully that answers it.
And Chris, I don't know if you can answer this next one as well, but why not use KD490 in a green band? Example given the VIIRS 555 nanometer.
The global KD diffuse attenuation coefficient of downwelling irradiance, that's what KD represents. The global data products that we're aware of and work with are generally provided as KD490, meaning diffuse attenuation coefficient at 490 nanometers. It would be better to use one closer to 532 nanometers, which is the wavelength at which ISAT2's ladder system operates. What we do is we actually provide a conversion from KD490 to KD532. And that's based on a derived empirical linear relationship between KD490 and KD532. That said, and I'm not aware of it, but if there is a global readily available VIIRS KD or VIIRS KD555, the question is a good one. That probably would be a better product to use.
Thank you, Chris. Question 23, can I get access to the data for Nigeria?
It is a global data set. So along the coast there, I don't know what the mask actually looks like in that space. So Chris, maybe at the top of your mind, you might have a better sense, but yes, what is available from finding bathymetry from ATL03 to ATL24 should be in that area.
All right, Diane, thank you. Question 24. Could this be used to map objects near coasts like vessels, buoys, jetties, etc.?
I wrote what is there, but Chris, you will definitely have a better sense of this because depending on the size of the sunken vessel, things like that, and the clarity of the water, being able to see that in the sea floor, I'm not sure if anybody has come across that in the tests, but possible if there isn't any turbidity in the water, I would think. Chris, I think you're still muted.
I was just saying I agree with Diane. It's really just a function of the resolution, and I think that one was addressed already. But basically, in the along any individual beam track, the resolution is approximately 70 centimeters. Although it also depends in the bathymetry case, it depends on water clarity, and then there's coarser cross track spacing. So, just is the size of an object, is it detectable at that spatial resolution? At least for things like jetties or large coastal engineering structures, if you happen to get a track line over it, you'll most definitely see it. And I've seen cases where you can get bathymetry right up to say a jetty, and then you'll see the surface elevations going over the top of the jetty.
Okay, Diane and Chris, thank you. Last question, 25. What happens in the presence of algae blooms or seagrass?
That's a great question, and I think the answer is it just depends. When you've got algae blooms, that's obviously impacting the turbidity, impacting the ability of that laser light to penetrate through the water column and to get a detectable reflection off the seafloor that makes it back up to the sensor. And then it's kind of a similar thing with seagrass. That can do a couple different things. It can obscure the seafloor. It also, seagrass tends to have relatively low reflectance at 532 nanometers, so it can make it difficult to get returns. But more commonly, what I've seen in areas, for example, we've looked at some data around St. Croix, where there might be a particular track that goes over a seagrass bed, and sometimes we have seen what looks like good bathymetry in those areas. I don't think we've done an accuracy assessment specifically over seagrass. So, how much does that impact the accuracy? I would say kind of unknown at this point, and probably depends a lot on, density of the seagrass, depth, and other factors.
Great. Chris, thank you so much. As we wrap up, I just want to thank, all the participants that joined, wherever you joined from. Thank you so much. We do look forward to seeing you in 2 days on Thursday for the second and final part of this training series. We also want to thank once again, Lori Magruder, Diane Fritz, and JP Swinsky, and also for those that were able to join to help answer the questions, Jeff Perry and Chris Parrish. Thank you both. And we also want to acknowledge Amy Neely, who's also helping out and supporting this training as well. So thank you to all the people that presented and also helped to answer the questions. And we look forward to seeing you all in 2 days for the second part of the webinar series. Thank you.